So, today we're going to dive into something really exciting, a revolutionary new blueprint for science education. It's all based on this landmark report that wants to take learning way beyond just memorizing facts and bring it into the real world of discovery.
I want you to think back for a second, back to your own science classes. Do you remember the endless vocabulary lists, memorizing the periodic table, or all the parts of a cell? Yeah, for a lot of us, that was science class. But here's the real question. Is that what science actually is?
Well, the framework that's at the heart of this new vision has a much more powerful idea. This quote just nails it. Science isn't just a random pile of facts. It's this dynamic, hard-won body of knowledge, and it's a tool for understanding the entire world. So how in the world do you teach that?
Well, the answer is a complete reimagining of science education. We're not just talking about updating a textbook or piling on more facts to memorize. Nope, we're talking about a whole new three-dimensional vision for learning and actually experiencing science. So what does a three-dimensional experience even mean, right? It means we stop treating science like a bunch of separate subjects and isolated facts. Instead, we weave everything together: the core ideas, the key ways of thinking, and the actual practices of scientists and engineers into one seamless learning experience. And here they are, the three dimensions in action. You've got the practices, that's what scientists do. Then there are the cross-cutting concepts, that's how scientists think. And finally, the disciplinary core ideas, that's the essential knowledge they build on. Now, the crucial thing to get is that these are not steps in a list. They're all interwoven, like strands in a rope, each one making the other stronger.
Okay, so let's break that down, starting with that first dimension, the practices. This is all about making a huge shift from learning about science to actually doing science.
Think of it this way. You wouldn't learn to be a chef by just memorizing recipes from a cookbook, would you? Of course not. You'd get in the kitchen, you'd start chopping, you'd mix things, you'd experiment. That's precisely the idea here. Students learn science by rolling up their sleeves and getting involved.
And where does all science kick off? With curiosity. This framework says that students absolutely have to learn how to ask good, meaningful questions about the world around them. Questions that you can actually investigate. Why do we have seasons? How do we get our electricity? It all starts with a question. Another key practice is developing and using models. And look, we're talking way beyond just little plastic models of atoms. Scientists create everything from diagrams and equations to super complex computer simulations to test their ideas about how a system works. It's a really creative process.
And this one might be the most important of all. Students learn to argue from evidence. See, science isn't about just blindly accepting what you're told. It's a process. You make a claim, and then you have to rigorously defend it with data and with logic. This is how scientific knowledge actually gets built and refined in the real world.
The framework also makes this really key distinction between science and engineering. While science is searching for that single best explanation for how something works, engineering is all about finding the best possible solution to a problem while dealing with real-world constraints, like cost and safety. There could be lots of good solutions, and the goal is to find the optimal one.
All right, so if the practices are all about doing science, our second dimension is all about thinking like a scientist. These are the big ideas, the mental lenses that connect all the different fields of science. This dimension is built on 7 of these cross-cutting concepts. I want you to think of them like a universal toolkit for your brain. It doesn't matter if you're a biologist studying an ecosystem, a chemist mixing compounds, or a physicist tracking particles. You are always looking for patterns, you're investigating cause and effect, and you're analyzing systems. These are the big ideas that bridge every single scientific discipline.
Let's just take one to see what I mean. Patterns. From the predictable cycle of the seasons to the phases of the moon, or even just the family resemblance you see between parents and their kids, recognizing and explaining patterns is totally fundamental to how we make sense of the world.
So that finally brings us to the third dimension, the actual content, the stuff you learn. But it's not just a long list of facts anymore. The best way to think of these core ideas is as the playground where students get to use the practices and the cross-cutting concepts.
This core knowledge is organized into these 4 major domains. But here's the magic. Instead of just memorizing facts about plate tectonics, for example, a student might now use the practice of modeling to understand the cross-cutting concept of cause and effect in earthquakes.
See? This is where all three dimensions snap together, turning static information into real, usable knowledge. Okay, so why does any of this matter? Why go through all the trouble of completely rethinking how we teach science? Well, the ultimate goal is so much bigger than just creating the next generation of scientists. Honestly, this quote from the report says it all. The goal is to empower all students. It's about creating citizens who can actually engage with science-related issues, who can critically look at the information they're bombarded with every day, and who can become lifelong learners. Bottom line, it's about scientific literacy for everyone. This is for absolutely everyone. It doesn't matter if a student grows up to be a scientist, an artist, or a mechanic. This approach gives them curiosity, critical thinking, and problem-solving skills. And those are essential for any path in the 21st century.
And all of this leaves us with one last, powerful question to think about. In a world that's facing some incredibly complex challenges, from climate change to public health crises, how will teaching science not as a set of facts, but as a way of thinking and doing prepare the next generation to build a better future?